on this computer. Okay. I'm going to record the seminar. Okay. So, can you see my screen, guys?
I can't.
Okay, so today I'm going to present some ideas about quantum field theory, okay, and machine learning. Yes, go ahead.
We cannot see your screen.
You cannot see. Okay.
No, no.
Okay, it's good. I have a problem with my computer escape. Sorry, guys. I have a problem. My mouse is not working. Okay. Screen share. Now, can you see my screen? I'm showing you. Okay. So sorry about the problem. Well, as I said, today I plan to present some ideas about quantum field theory and neural networks. Let me begin by saying that I am not an expert on neural networks, but I'm very interested in learning about neural networks and quantum field theory because right now this is a very important research area. So I divided my talk into 3 parts. In the first part, I plan to comment about this paper. This is a very nice paper, Quantum Field Theoretic Machine Learning. This paper was published in Physical Review D in 2021. So in the first part of my talk, I plan to present the basic aspects of this paper. In the second part, I plan to talk a little bit about the projects that I have in mind about this area. And finally, I want to present some notes about theoretic quantum field theories and neural networks. So let me begin with this paper. Okay, I'm going to describe the main result of this paper. In the first section, is called the 5-fold scalar field theory as a Markov field. So this is some notation. G, this calligraphic G, is a graph, is an unoriented graph. Lambda, capital lambda, is the set of vertices, and E is the set of edges. G is a finite simple graph. Okay, let me. Okay. So if I and J are 2 vertices, sorry, if there is, yes, if I and J are 2 vertices, there is, and there exists an edge, there is a typo here, E, between I and J, then we say that I and J are neighbors, or that they are adjacent vertices, okay? So neighbors means that there is, I and J are neighbors if there is an edge connecting them, okay? I'm going to denote by Ni the set of all neighbors of the vertex I. Now I need this notion. A clique is a subset of the set of vertices where all the points are pairwise connected. Oh, there is a typo here. So a clique is not a subset. This is a typo here. A clique is a subset of the vertices of a simple graph such that every 2 distant vertices are adjacent. Now, let me show you an example. This is a graph. In this graph, this set is a clique. Why? Because any 2 vertices in this set are connected by an edge. Now, if we include an additional point, for instance, if we include this point. Now this set is not a clique. Why? Because there is no an edge connecting, for instance, these two vertices. Okay. This is another example of a graph. I'm probably going to go back to this example in a minute. Okay, a clique is called maximal if no additional point can be included, such that the resulting set is still a clique. Okay, so here you have, this is an example. I already mentioned this. This set is a maximal clique. Okay, it is not possible to add an extra point to this set, and such that the resulting set is still a clique. Okay, now we associate to each vertex a random variable. See, then phi I is a random variable, is the random variable attached to the vertex I. This collection of random variables, where this index I runs to the vertices of the graph, is called a configuration or the configuration of the system. Okay. So given a graph, the set of random variables, this set of random variables, define a Markov random field if the associated probability distribution P, this is the distribution associated with these stochastic processes, fulfills the local Markov property with respect to this graph. Now let me define this. The local Markov property with respect to this graph is defined in this way. The probability of phi I given all the variables for J belonging to the set of vertices except the vertex I. This conditional probability is exactly equal to the conditional probability of phi given the variables, the knowledge of the variables when J runs through the neighbor of I. Remember that this Ni denotes all the vertices in the graph which are connected to I. So this is the Markovian property in this frame. Okay. Oh, by the way, guys, if you have a question or a comment, you can interrupt me at any time. There is an important result called the Hammersley or Hammersley for theorem. This theorem says the following: a strictly positive distribution P satisfies the local Markov property of a simple graph G if and only if this distribution can be written as a product of this form. In this product, this C denotes a clique, and this C runs over all maximal cliques of the graph. This function psi of C is a potential, is called a potential, it's a strictly positive function, okay? There is one of these functions per clique, and this constant Z is a normalization constant, and this normalization constant is defined in this way, okay? So this theorem gives a test to check if a positive distribution on a graph satisfies the Markov property. Okay. So in the paper, the authors were with the square lattice. So the authors in this paper, the authors work with a lattice of this type. Okay. So the next step is to introduce a lattice action. So basically, this is a lattice action. This is an energy functional defined on the fields phi. So in this expression, theta is a parameter. So this is the action. There is a sum. The first sum runs on the adjacent vertices. Okay. These W, I, J are parameters. Okay. AI is a parameter and BI is a parameter. So this is given a configuration of the system. Remember, the configuration is given by phi, and we are identifying phi with this vector. This function associates to this configuration and energy. Okay. I'm gonna theta is the set of parameters in this action, in this energy functional, and theta is defined in this way. From a physical perspective, the parameters theta are the coping constants of the quantum field theory. Okay. Now, we attach to the energy functional this Boltzmann probability distribution. Boltzmann or Boltzmann's gives probability distribution. So the probability is exponential minus the energy of the configuration divided by this constant. This constant is typically denoted as C. Okay. And this constant is called the partition function of the system. So this is the Boltzmann probability associated with the system. Okay. Now, this is just an observation. Really, this integral is just a sum because we are working with discrete functions. So this integral is really this sum. Okay. Now, a 5-4 quantum field theory is defined by this probability. In other words, given a phi-4 lattice field theory is equivalent to give this probability distribution. Now, an important observation is the following. For a square lattice, only the nearest neighbors define a maximal cliff. So in this paper, the authors were with a square lattice like this. If we fix a vertex I, then J1, J2, J3, and J4. This is the neighbor of I, and this set is a cliff. Okay. Then it is easy to verify that the Boltzmann probability, this Boltzmann probability satisfies the Hammersley, let me go back to show you the, satisfy this theory, Hammersley or Hammersley Clifford theory. Okay? It is very easy to verify this. Why? The reason is, this is the main reason. Okay, now, we have to construct for each maximal cliff, this is a maximal cliff. We need a potential, which is basically a positive function. In this case, we use this function. Notice that here we have some new constant, 1, 4, and we have these new terms. Okay, notice that basically ij, phi sub I squared is exactly this term. When we sum over the neighborhood of the points in the neighborhood, basically these, we have 4 terms. So basically this term disappears. Now, there is a result that says that it's possible to multiply a potential function with a strictly positive functions of subsets of the cliff. So basically, this function phi is obtained from is a part of the exponential of the energy. Here we have by the energy. It's a part of this exponential multiplied by the exponential of aj phi sub j squared. And this multiplication is acceptable. This multiplication doesn't change the Hammersley-Clifford theorem. So for this reason, the Boltzmann probability distribution can be written in this way. Okay, this means that the 5-4 theorem corresponding to this Boltzmann probability satisfy the Hammersley-Clifford theorem, and then this random process is a Markov field on the graph G. Are there comments or questions? Okay. Now, the next section. In the next section, these authors, the next section is called Machine Learning with the 5-4 scalar field theorem. Suppose that Q is a target probability. In this framework, Q is the distribution, is the probability distribution of an arbitrary statistical system. This is the Boltzmann distribution of other statistical systems. Okay. Now, the goal is that the 5-4 neural network attached to this Boltzmann distribution learns this new probability distribution. In order to do this, we need an algorithm to select the parameters theta so that this distribution is very close to the target distribution. Okay, so we need a notion of distance. So we need a distance measure between the probability between these two probability distributions. Okay. The Kullback-Leibler divergence is defined in this way. In this notation, P and Q are probability distributions. So the Kullback-Leibler divergence is defined in this way. This is integral, this functional, it gives a non-negative real number. Okay, this Kullback-Leibler divergence is zero if and only if the probability distributions agree, but the Kullback-Leibler divergence is not symmetric, and the Kullback-Leibler divergence doesn't satisfy the triangle inequality. So in conclusion, this functional is not a distance, but it is very useful. Okay, so we're going to use this function. If we define this function, notice that here we have the Kullback-Leibler divergence of P and Q, and let's say the reciprocal of the Kullback-Leibler divergence of Q and Q. This functional defines a distance. Okay. Now, by searching for an optimal set of parameters, we can minimize the Kullback-Leibler divergence so that the probability distribution of the 5-4 scalar field theory will converge to the target probability. Okay, so we need an algorithm to perform this task. Okay, now, after getting this probability distribution, notice that at the end of the learning process, we obtain a set of parameters. Okay, so we have a probability distribution. After getting this probability distribution and using the Markov chain Monte Carlo method, it's possible to draw samples that would be representative of the target distribution. The idea is that this probability distribution is very close to the target distribution. So by using this method, I do not know this method. I do not understand this method. By using this method, it's possible to obtain samples of the target distribution. Of course, using this distribution. Now, in this paper, the authors studied the case in which the target distribution is a Boltzmann distribution. So in this case, this calligraphic A, represents an action of a certain physical system, and this constant is the partition function of the system of the system A. Okay. Now we use the Kullback-Leibler divergence. The Kullback-Leibler divergence between P, which is the Boltzmann distribution of our 5-4 neural network, and this is the target distribution. We know that this is a non-negative real number. So if we replace P and Q in this expression, we get this formula. We get minus the natural logarithm of ZA. Remember, ZA is the partition function of the system A. This is the energy functional of the system A. This is the energy functional of the 5-4 neural network. This is the average with respect to this probability distribution minus the logarithm of Z, where Z is the partition function of the 5-4 network. Now the point is that this function is the free energy of the system. Okay, so we are going to use f of A to denote this function, and F is the free energy of the 5-4 network. So this inequality can be written in this way. Now we call this function F calligraphic F. Okay, and this inequality implies that it's possible to minimize this free energy, and then it is possible to approximate the target probability distribution. In order to construct an algorithm, we use this function. Indeed, we need the gradient of this function with respect to the parameters. Okay. Then the parameters are updated using this algorithm. T is the time, so in the time t plus 1, the parameters of the network are updated using this rule. We use the parameters of the time t minus this expression. This is a constant. This is the so-called learning constant, and this is the gradient. Okay. It is expected that this algorithm gives a very good approximation of the free energy associated to the target distribution, and then the Boltzmann distribution of the 5-4 network with the right parameters. Here we have to use the parameters obtained by using this algorithm. So if we use the right parameters, then this probability distribution must be a good approximation of the target distribution. This means that the network, the 5-4 network, may learn this distribution. Okay. Comment or question? Now, in the next section, the authors discuss learning with predefined data. The preceding results do not require any predefined data to be used as input within the training process, since the configurations were obtained during the gradient-based approach. I understand. My understanding of this paragraph is the following. But remember, I am not an expert on neural network. There is a chat. Okay, right. If you have questions, please, it is better if you ask the question aloud because I am not checking the chat. Okay.
Dr.
So this is
Zúñiga.
my understanding. At the time t,
Dr. Zúñiga.
yes, go ahead.
Real quickly, I was just wondering, the learning constant, I think it was eta. What effect does, what does the learning constant do actually? Like, what effect does it have?
Okay, as far as I understand, this constant control how fast the learning process occurs. So it is very important to select this constant carefully. Okay, but honestly, I haven't implemented a neural network. Okay, so this is the knowledge that I have about this concept. Okay, now yes, I understand. I mean, this part, in this part, the authors are describing the implementation, the implementation of the network. So honestly, I don't have experience implementing this type of machines. Okay, I understand the following. At the time t, we know these parameters. This is the version of the parameters of the network at the time t, and of course, we know this probability distribution. Okay, now we draw, using this probability distribution, we draw samples for these variables, okay, using this probability distribution. With these samples, we can compute this energy function, because in order to compute the action of the energy functional, we need, let's say, the fields and the parameters. And then we can compute these free energies. And then we can update the parameters using this approach. Okay, using this approach. Okay, this is my understanding of this paragraph. But as I said, I am not an expert on this matter. Okay. Now, in this paragraph, the authors assume that a data set is given. This data set given encodes an empirical probability distribution. We call this probability distribution Q. Okay. Also, we assume that this probability distribution is a good representation of the complete probability distribution of the system. In other words, this means that we have enough data such that that the data given is enough to provide a good representation of the probability distribution of the unknown system. Okay. Now, the empirical distribution can be learned by minimizing the divergence. Notice that now we are using a different pullback label divergence. Okay. Notice that now we have Q first and then P. Okay. Again, we replace Q and P, and we get now. Let me put this. We get this expression. Okay. The point is that the first part is constant. This is an average with respect to the data. So this is a constant. Okay. So this is the important part. Okay. The minimization of the Kuppel-Leibler divergence is equivalent to the maximization, because there is a minus sign here, of this function. So we have to maximize this function. So the minimization of the Kuppel-Leibler divergence is equivalent to the maximization of the second term in this formula under training data. This function, the logarithm of this probability distribution, is the so-called log likelihood function. Okay, so it is possible to compute it. In order to use, we need the gradient of this function. So it is not difficult to compute this gradient. Now, using this gradient, we can update the parameters in this form. Okay, so these are the parameters at the time t+1. This is the set of parameters at time t. This is the learning constant, and this is the gradient of the log likelihood function. Okay. comments or questions? This is, this is a summary of this paper. Okay. Now, I want to describe briefly some projects about neural networks in the p-adic framework. I am working in 3 projects right now. The first project is called p-adic cellular neural network. It's a joint project with Brian Zambrano Luna. In this project, the neural networks are described by integral differential equations of this form. Capital X is the state of the let me try to so a small x represents a neuron, and the capital X represents the state of this neuron. Okay, so this integral differential equation describes the behavior of the network. Notice that here there is a function y. This function y is the output. The output is obtained by passing the state, this is the state of the network, by passing the state of the network through a nonlinearity. F is a nonlinearity, typically a nonlinearity of this form is used. Okay, so we are studying these networks. There is a preprint. We already published or uploaded a preprint in the archive. This is the record. Okay, now this is the classical perception. This is the most simple neural networks. In this case, there are n entries, x1, x2, xn. Okay. W1, W2 are weights. Okay. So here we have this sum. Okay. This sum represents a sample, a weighted sample of the inputs. Now we pass this weighted sum through a nonlinearity, and then we get y, which is the output of the network. Notice that in this case we have input and an output. Okay. Now it is possible a natural p-adic version of this perceptron is given by an expression of this form. Now we replace this sum. We replace this sum by an integral. Okay. In order to get the output, we pass this integral, this continuous sum, through a nonlinearity. X, capital X, is the input, and Y is the output. Of course, in order to use this p-adic version, we have to discretize this integral, and a suitable discretization process will produce an expression of this form. The difference is now, in the p-adic case, these variables are ordered, or these variables form a rooted tree. Okay, this is an interesting problem, and I suggested this problem to Mr. Diva. Okay, now, by the way, it is important to know that many years ago, Andrei Krenikov and Sergio Alveverio, this is an old here, and another folks, wrote some papers about p-adic neural networks, but these neural networks are completely different. Now, I am also interested in the connections between quantum field theory and neural networks. This is the title of this project. And there are more problems. For instance, it is possible to study stochastic neural networks. So basically, a stochastic neural network is given or is controlled by an equation of this form. Notice, in this case, X is the state of the system. At the time X, this capital X is the state of the system. This is the so-called Vladimir-Kyrilson operator. Then this equation is the heat equation in the periodic world. By heat equation, I mean that there is an stochastic process attached to this equation. Now you see here, we have this integral gives a sample of the state of the system at the time t. This is a bias. And now the new part, this is a noise. Okay, this is a noise. This is the stochastic part. And the output is obtained by passing the state of the network through a nonlinearity. So F is a nonlinearity. So right now I'm interested in this process. Okay. Now let me check the time. Now I want to present some ideas about 10:37. Yeah, I have 10 minutes. I want to present some ideas about quantum field theory and neural networks. Okay, this is a title. This is a provisional title: Theory, Convolutional Neural Networks, and Quantum Field Theory. So let me review some ideas about theoretic numbers, because there are maybe there are some folks that do not know or do not remember this definition. So P is a prime number, okay? The field of theoretic numbers is denoted by QP. This field is defined as the completion of the rational numbers with respect to the theoretic norm. This is the symbol of the theoretic norm. The theoretic norm is defined in this way. If X is a rational number, if X is 0, then the theoretic norm is 0. Otherwise, X can be represented as a power of P times a fraction where A and B are not divisible by P. Then this gamma is unitely defined by X. We define the theoretic norm as P to the minus gamma. Notice that if X is an integer highly divisible by P, then the theoretic norm is very small. The integer gamma is called the theoretic order of X. By definition, the theoretic order of 0 is plus infinity. Okay, so the completion of the rational numbers cubed with respect to this theoretic norm is the field of theoretic numbers, denoted as QP. Any theoretic number different from 0 can be represented as a convergent series of this form. Okay, in this series, the digits, the X, J are theoretic digits. So these digits are elements of this set. I am taking X0 different from 0, then this number, this integer number, is well defined. This number is the theoretic order of X. Okay? Any theoretic number different from 0 can be represented as a power of P times a theoretic number Vx, and the theoretic norm of V is 1. QP is a metric space. Then we can define the ball with center at A and radius P to the R in this way. So this is the ball. The ball is the set of all points in QP such that the distance from X to A, of course, the theoretic distance, is less than or equal to P to the R. In this way, and this is the definition of the sphere with center and A and radius P to the R. Okay. As a topological space, this metric space is totally disconnected. This means that the only connected subsets of QP are the empty set and the point. Okay. This space is a locally compact topological space because the balls are compact subsets. Okay. Then, if we consider QP with the sum, we obtain a locally compact topological group. Then by applying the hard theorem. The hard theorem says that there exists a hard measure. So that there is a hard measure, okay, denoted by this symbol, which is invariant under the action of the group. Symbolically, we denote this part in this way, okay? We normalize this, or we pick this measure so that the volume of the unit ball is 1. Okay? Now, let me define some function of the Bourget-Schwarz space. So here, we work with functions from, let me change the color. From functions from QP to C, okay? A complex valued function phi defined on QP is called locally constant if for any point in the domain there is an integer depending on L such that the restriction of this function to a small ball is constant. Okay, the meaning of this formula is the following: if x prime is a small perturbation, if we take a small perturbation of the argument, then the value of the function doesn't change. For this reason, we say that this function is locally constant. Now, we say that phi is a Bourget-Schwarz function or a test function if this function is locally constant with compact support. Okay? Any test function can be represented as a linear combination with complex coefficient of characteristic function of both. Okay? I use this symbol to denote the C vector space of Bourget-Schwarz function. And I use this symbol to denote the real counterpart. Okay. Now, if phi is a test function, then phi has compact support, and then by a simple argument, it is possible to show that this number L can be chosen independent of the function. The largest L satisfying this condition is called the exponent of local constancy or the parameter of local constancy of the function. Okay. Okay. Let me define this. If U is an open set in QP, this symbol, DU, is the C vector space of all test functions with support in U. This space is dense in L2 of U. This space L2 of U is the set of all complex valued functions defined on the set U with this node, with the standard node. Let me check the time. Okay, now, let me probably let me stop here, stop. Guys, it's almost 11, and I have 15 more pages. Probably it is a good idea to stop here and continue the next week. What do you think? Because otherwise I have to run, and it doesn't make sense, you know. We have time. Do you agree? Guys.
I think that's a good idea.
Yeah, because
Yeah,
otherwise I
good.
have to run a lot, and it doesn't make sense. Okay. So,
but this is,
I'm gonna stop
I want to
here.
thank you. This is beautiful. What you've presented is beautiful. I really love it.
So I'm in the coming week, I'm going to discuss some ideas about the p-adic version of these quantum neural networks. Okay. So I prefer to stop here. If you have questions or comments, please go ahead. Okay.
I may need to save one or two of my questions for next time, but it's interesting because it looks like they're still doing this gradient descent that you normally do in these, but it's somehow, I think there's a lot more connectivity in how that's done, it seems, because you're not just going through one level of a neural network.
Yes, you're right. I mean, really, this is a search in a space of high dimension.
Right.
Yeah?
Right.
So there are many. Yeah, go ahead. Dude.
Oh, so I'm curious because there's a paper. I can't remember the. Kochube, I know was Kochube was an author, and I think it was. I can't remember. I can't remember the reference to the paper, but it's on a phi4. I think it's a phi4 quantum field theory in the.
No, there are many papers about.
Yeah.
About 5-4 quantum field theory over the PIs. Many papers.
But somehow this is like this is a discretization of that, and
exactly.
And I wonder if there's sort of a way of understanding the continuum limit.
Exactly. That's yes, you are right. You're right. So I'm gonna discuss that in the coming week.
Great.
Basically, we had to start with a continuous model. Okay, with a continuous model. And then by a discretization, we get an action similar to the one used by this guy in the paper that I present. Okay, then there are several problems that we can study the continuous version of the network. This is a difficult problem because, you know, in this case, you really have to construct a quantum field theory. This is quite complicated, but there are many results in this direction. Or you can work with the discretization. The discretization is simple because in the discretization we don't have the difficult problems that we have to face in the quantum field theory. Okay. In addition, for practical purposes, we have to use discrete mode. So I'm going to try to discuss these ideas in the coming week. And of course, there are many problems there. There are many difficult problems. And there are more articles. I selected this article because this is very simple. This article that I presented is very simple. There are more technical articles. But I think that for a first presentation, it is a good idea to pick the simplest article also. Okay? But yes, that's the idea. We start with a continuous model, then we obtain a discretization, and there are many problems connecting quantum field theory with these new objects. Okay? So I'm going to present this in the coming week.
Wonderful.
Okay. So your talk is not for the coming week. Okay.
That's wonderful. Thank you so much.
Okay. Okay. Thank you, guys. Okay. Do you have more comments or questions? Nathan, your microphone is off, Nathan.
No, I was just saying I enjoyed it. It was a great presentation.
Yeah. So sorry about the typos. I didn't have time to prepare slides. For this reason, I just wrote some handwriting notes. Okay.
Actually, I loved it. It was great. It was perfect. It's great.
Okay. Thank you. Thank you, David. Veselin, do you have a comment or a question?
Yes. So first of all, I want to thank you for the introduction to p-adic numbers, since maybe some of you are new, including me. I just have one question. Maybe you'll discuss that next time, but is there any advantage in quantum theory considering p-adic numbers than rational?
Okay, that's a good question. Well, let me tell you something. Really, the relevance of studying quantum field theories over p-adics is that in the p-adic world, there is no order. The field of p-adic numbers is not an order field. Okay, the field of real numbers is an order field, and then in physics, causation depends on order. We say that an event occurs before order because we have order. So these theories, the p-adic versions, are non-causal theories. Okay. Because it is not possible to introduce an order. And this is interesting in physics, okay? I have written some papers in this direction, and it is possible to construct, one important thing that it is possible to construct rigorous, mathematical rigorous quantum field theories. A quantum field theory is basically a measure, a probability measure in a space of infinite dimension. okay, or a stochastic process in a space of infinite dimension. In the p-adic case, it is possible to construct in a rigorous way these quantum fluid theories. Okay, but that's the main interest. From a mathematical perspective, it is completely natural to study quantum field theory over p-adics, because p-adics are a good space. In terms of probability, the p-adic space is a Polish space, and Polish spaces are the best spaces to do probability. Okay, so it is quite natural to do probability on p-adics.
Okay, thank you, sir. I'll pay attention to that next time.
Okay, no problem. Okay. Okay, guys, I'm gonna stop here. So let me stop recording.